Hi, good afternoon, everyone, and welcome to the Water Tower Research Fireside Chat Series. We're very excited to have with us today Dip Patel, who's a Chief Technology Officer of Soluna Computing, which is the operating subsidiary of Soluna Holdings. My name is Graham Mattison. I'm a senior analyst here at Water Tower in our Sustainability and Industrials practice. As a reminder, this call and all of our research is open to the public and available for everyone. And we will be doing a follow-up note after this call. And again, those can all be found from our website at watertowerresearch.com. We will be taking questions from the audience, and those can be submitted via the webcast. Hopefully we'll have time to get to all of them, but if time does not allow, our apologies if that's the case. So as a quick background, Dip has been the Chief Technology Officer of Soluna since 2018, having previously founded and sold a company called Ecovent Systems, a climate control company. Early in his career, he worked at Lockheed Martin, focusing on the ballistic missile programs, and then also the advanced radar and electronic warfare systems. He is currently also an entrepreneur in residence and a lecturer at the Massachusetts Institute of Technology, and also a diehard Eagles fan. So we know which team he's pulling for this weekend. So with that, Dip, thank you very much. I'll start off with the first question. What brought you here to Soluna? And coming out of your last venture, you must have had a number of opportunities that you could have gone given your skill set. What is it that that attracted you to Soluna, to this whole opportunity?
Yeah, I'll tell you, part luck and part intersection of interest, right? So I've always been into Bitcoin since it was launched and the mission of it was made clear. I thought it was very interesting. But I would say that the thing that most tied to it was the climate impact piece. You know, I left Lockheed to start Ecovent to focus on the climate, and this was a natural segue to that. And then tying to that was just John Belizaire, right? When I was building Ecovent, he was a mentor of mine. When I sold it, he helped me through that process. And when I knew he was starting a new company, he wrote me an email, and he just basically the subject line was, "Who do you know that knows about crypto?" And I was like, whatever he's into, I'm getting involved. And that was the end of it. You know, he wanted an introduction to a CTO. And I said, no, I won't be introducing you to anybody. Not until I get a chance to understand what you want. And then, you know, the rest is history.
Great. What has been different about the industry and this opportunity than you first expected when you joined?
You know, when the internet was launched, or like when it not launched, but let's say when it started becoming more mainstream, right? Late 80s, early 90s, I was a kid, and I got to see it as a spectator, and I saw the birth of a new industry, these little communities, you know, and incredible niche ways of the internet being used. It started with bulletin boards and Usenet, ended up with the web, and now streaming and all this amazing, it's the backbone of the world. Digital currency and crypto is the same way. It started with all these tiny, beautiful little communities that were working on really neat things, and they were driven by high passion. But then the industrialization happened, right? These things started getting bigger. And what happened, just like with the internet, what happened is larger companies, larger institutions started coming in that brought more discipline, more rigorous application of capital and growth, right? To bring standardization and to bring some credibility to the whole game. Now, the issue with that is, you know, in the internet piece, that was driven by technologists, right? It was a bunch of nerds who started to the telecom industry, and most initial big web companies were technical people and technical operators, right? But what I've noticed in this space is a lot of the industrialization of it is being led by capital first. And then the people that kind of monitor that capital usually have backgrounds in capital or backgrounds in consulting or backgrounds in business, not as many backgrounds in pure operations or pure technology, right? And so what you've got is the business sense of it coming very, very, very nice and disciplined, which is driving amazing analytics, metrics, and standardization. But what it means is the people who can operate, they're going to be incredible. And that really makes me happy, because one of the things I think that John and I pride ourselves on is that we're operators, right? We want to get our hands dirty and get involved. And I think that what's happening is the operating people, what you're seeing during this downturn is the operators are the ones that are kind of emerging, right? And that's going to be fantastic for the industry as a whole.
Got it. You probably also didn't expect how long it takes to get anything done in the electric power world either.
Well, everybody warned us, I remember
but
when
you
we were
can't
working,
imagine it until you go through it yourself, where you're like, I can't believe it's taking so long. But it's just, this is an industry where, anything other than 100% uptime is complete failure. So they're so cautious.
Oh, totally. And, when it comes to these kind of loads, the grid doesn't know how to evaluate it, right? So just figuring all of that out. And it's funny, we thought, moving from Morocco to the United States, because, Soluna started with the Moroccan wind project. We thought, okay, this is going to go faster. And it did, right? It's still much faster because we're in the country. We know how to do business here and all of that. But you're right. There's just so many complications and moving parts to interacting with the grid at this scale. And you have to really understand it. And when it's a new business model, a new way of using the energy, people are ultra cautious, especially with what's happening, with the climate and the stressors that the grid is feeling right now.
Oh, yeah. And in
more
Texas,
green
you're
energy
coming out of that. Yeah. And in Texas, you're coming off the heels of that ice storm that took so much off in this national headline.
That's right. That's right.
So another question, can you talk about Soluna's modular data centers, just in terms of how you design them and why you design them that way, and then maybe talk a little bit about how they compare to other data centers that are out
there? Yeah, so the thing is, my background as you brought up earlier, thank you for that. It was very kind. Came from building radar, right? And wireless systems. And in those systems, efficiency is everything, right? The more efficient you are, the farther you could see, the longer you could see, so on and so forth. And so when we came to this industry, we weren't looking to build a data center, right? What we were looking to do is solve a problem. And that problem is that the more green energy you integrate into the grid, the more asymmetrical power problems you create, right? When the wind is blowing, people are sleeping. And so unless the Eagles keep winning Super Bowls and getting there, the energy use won't catch up in the evening that the wind produces. And so the concept of the data center was, okay, can we use computers to consume just that energy? And if we were going to do that, and Bitcoin was an obvious first choice, but it was never just Bitcoin, right? It's moving into AI and ML. So we looked at AI and ML machines, computers as a whole. And what we learned was, hey, there's a whole bunch of compute that you can turn on and off, and it's okay, right? And if we use that and marry it to a data center, all of a sudden we can solve a lot of problems. So what makes that system the most efficient is what we started with. And in order to do that, you say, okay, these things are remote. They have to be easy to construct, easy to operate. They have to be very efficient because, you're basically trying to not consume water, right? Because you're remote. And so you need to be ultra efficient. Otherwise, there's too much heat in there. So when you do all of that, what you do is you design basically with a blank slate what looks like a radar system, but it's a data center. And a big piece of that is you'll notice computer chips, they're starting to operate at hotter and hotter temperatures. Even Equinix, right? One of the biggest data center companies that prides itself on latency is starting to run their data centers hotter. That's a huge seismic shift in thinking. And so when you take all those things and you mash them all together, right? The need for asynchronous compute, the need to consume random power in the middle of nowhere, the need to be able to do this efficiently, and the fact that chips are hardening to more, let's say, less stringent requirements. Again, all requirements that we dealt with in the military, right? As we started deploying in the desert and things like that. What you do is you'd create a data center from scratch that can do that. And that's what we designed. We threw away all of the initial design assumptions that data centers have, right? You have to have multiple, power sources. You need to have temperatures of 70 degrees going into your computer, right? All of these requirements. We said, what if we didn't do any of that and just add the requirements that you need? And when we did that, we designed what you see here. And the beauty of it is, you know, when you design a radar, a lot of it is done on the computer, right? Like it used to be pen and paper. Now it's simulation software, incredible simulation software. So it's the same models here, right? Those simulation software that we used in radar 20 years ago, 15 years ago, is now accessible to people like us at Soluna, right? And you can log on to Onshape or SolidWorks, and you can do all of these crazy simulations. And we had real world data centers that are operating. So we use the real world data to feed our simulators, and we built a simulator the same way we did for radar for the data centers. And that's how we were able to fine tune the entire design before we ever built one. Then we built one and we fine tuned it even more, you know?
So what were some of the challenges that you ran into in terms of making the changes from when you first started to where you are now?
Well, you know, one is that what you want to do when you're doing something new is surround yourself with the best experts, right? The best team, the best people who can help you avoid unoriginal mistakes or unoriginal mistakes, right? You want to make original mistakes. And so the problem with this is every time we met new people and we tried to explain this data center we were trying to build, and we knew a lot of them, right? From my background through my MBA program, a lot of folks went into the data center space. My brother's in the data center space. And John obviously is, you know, telecom and software maven. So he has a lot of contacts. And everybody we talked to basically was like, what are you doing? Come again? Are you crazy? Like it took so long just to get people who were open-minded enough to recognize that something like this could actually work. And those are the people we kind of created partners with. So, you know, I would say that just finding the people who had the intersection of this amazing base of knowledge that's just impossible to simulate or learn quickly, but also, you know, the open-mindedness to change the way they're thinking into maybe a new way is very, very not hard. It takes a longer period of time to find those people, right? And more punches in the face. And luckily I got to deal with that at Lockheed, right? Because we were shifting away from missile defense where you hit a missile with another missile, right? To electronic warfare where you're confusing the other missile. And, you know, when you're trying to convince the military that's used to hitting things, hey, just confuse it. It requires a change of thought. So it's not necessary. And John had did this in insurance, right? Entrepreneurs do this all the time. So it's not that it was impossible to deal with. It was just, it was everywhere because the energy people didn't want to see it and the data center people didn't want to see it, right? So it was and then you would layer on crypto on top of that, and it adds a whole nother layer of Venn diagramming, right? So
Yeah, exactly. So now, I mean, this would be your fourth, you know, go looking at Dorothy, this would be probably your fourth setup as you're looking here. And in the case of Dorothy, which, you know,
so cool.
the company is fine, you know, getting closer, and there was some great news out earlier this week that you're in the final stages with ERCOT. But how have you been approaching the technology for the Dorothy project?
You know, the F-35 program in the military gets a lot of flack because it's very expensive, and it's been going on for a while. But you know, the thing is, it was revolutionary in that what they did, what's called concurrent test, right? They were building the flight manual for the plane while they were figuring out how to produce it, right? And that shaved decades off the time to market, so to speak, for this aircraft, right? And we had to do the same thing at Dorothy, right? We have this data center that we're building that has to interact with the grid, interact with the wind farm, and interact with pricing signals and all kinds of things, and then turn on and off based on a set of requirements. And there's really no way to test that until you build it, right? So what we did was we built a digital twin. We literally built an entire simulator of Dorothy, right? The switches, the power supplies, the power distribution units, the transformers, the fans, all of those things were characterized with real world data captured in Kentucky. Then we built a digital twin, And then we use the algorithms, the control algorithms that we're going to use to turn on and off Dorothy, the network, all of that against that simulator, right? And what that's allowed us to do is, and then once we knew that worked, we actually started controlling the Kentucky site using the Texas data to prove that our algorithms all made sense, right? Because the thing is, in Kentucky, the utility gave us about 3 months to make sure all of our algorithms were working when we turned on the site before we were tied to that power purchase agreement. In Texas, as soon as we turn on, we have to adhere to the rules of the grid, right? And so that code better work. And the code is designed, first of all, the code is always designed to fail off. So if anything is out of whack, the site shuts down, right? So that's always good. But the beauty of it is we've been able to de-risk it component by component completely on the cloud. And we've created this digital twin technology that we could use at other sites in the future as well. And what that allows us to do is concurrent test, right? We can test out all of our switches, our networks, make sure all the control algorithms, the APIs, everything is working on time and exactly right. And we're using real data, right? The data is available on what the grid is doing. So we pull that, we put it into our twin, we make sure the twin does what it's supposed to do. And then when it comes time to bring it online, that's when you just plug it into real miners and you see, you make sure everything is working there.
Was that helpful having that data when you were dealing with ERCOT in terms of getting them comfortable with your technology?
Oh yeah, we used to run these. I mean, we still do. We run a demo with these partners who they get to come online and they actually take down. They actually see the site running, hear it, and then they hit a button and they can see it shut down and hear it shut down, and then hit another button and see it turn on. And that reaction, just feeling it, really adds a lot of credibility and trust, because these folks that operate the grid down there, right? They're responsible for huge amounts of area and land that have customers that need power. Their livelihoods depend on it, right? So,
or lives in some cases. I mean, that's it. If it goes wrong, it is life or death in a lot of cases.
Yeah, and we want to respect that. And the only way to do that is make sure our tech works. So if there's a blind spot, we want to find it. And that's why this digital twin technology and having a real data center in Kentucky, as well as having a partner in Texas, the ERCOT grid, and all of our grid partners. It's not just ERCOT, it's all of the co-ops. All of those folks are just incredible partners to work with. And that allows us to build this tech in a very stable way.
Great. Shifting gears a little bit, as you look at the technology that you're putting into the data center, does it matter to you, or do you approach it differently, whether or not you're going to be hosting third-party miners there versus generating Bitcoin or doing the computing for yourself?
In many ways, no, but in many ways, yes. It's almost like if you have an apartment. This analogy just came to me, so I hope it's cool. But if you have an apartment, you wanna bring it. Let's just say it's like a 2-floor multi-family apartment, and you want to rent the bottom unit on Airbnb, right? There's certain protections you have to put in place for both the person renting it as well as you. And that's how you approach it, right? So it's almost like we're hosting from ourselves, right? And we have a set of requirements as hosting clients, as mining operators. And then we have a set of requirements as the technical people running the data center itself, right? And they have to match. When we bring in a third party on that, what we need to do is add in that third set of requirements, right? As well as the applicable firewalls, right? If these customers want to come in and look at their miners alone, but they're physically connected to the same network, you need to have all of these appropriate controls and firewalls in place, auditing, right? Customer support. If our ops team doesn't like it, they just hop onto Slack and say something. If a customer doesn't like it, they have to have a mechanism to say that, right? And so all of those things are taken into account. And luckily, we've architected our software in such a way that makes those types of things not easy, but straightforward to implement. But you have to be thoughtful,
Now you set it up. And again, for just a reminder to the audience, if anybody has any questions, those can be asked via the webcast. Question that Bitcoin's seen a great start to the year, but last year was certainly a challenge, and there were a number of bankruptcies in the industry. How has the marketplace shifted or changed or evolved for technology out there? And as you changed your approach to how you look at it, given these things?
Oh, well, for technology, what you find is that as the markets, yes, have shifted, but if you look at the hash rate, the amount of miners out there, right? It hasn't 100% correlated, right? When the markets are down, it's not like everybody unplugged. And what that means is that more and more thought has been put into efficiency, right? And so there's lots of amazing new software, analytical tools that are being released, like firmware for miners, things like that. And so the technology itself, I would say that it evolves differently, right? When it's a bull market, people are looking at, okay, how do I get more hash rate out of my machines? How do I cool them faster? Right? How do I just supercharge everything, right? When the market's down, you might tune it to, rather than pure horsepower out of each machine, you look at efficiency, right? Joules per terahash. How much energy does it take for a given unit of compute? And you want to optimize for that ratio, right? And so firmware might allow you to tune those things, and decisions being made might allow you to tune that. So I would say that, and remember, I'm not studying the markets. There's a lot of smarter people at Soluna that do that and explain it to me. I'm more looking at the technology, the mining stack, the efficiency stack, of converting a watt to something useful. And for us, what that's done is given us more options on the software side, right? And the other piece that again is, I mentioned it earlier, right? Equinix is raising the heat on their data centers to save, to curtail power and become more efficient. That's being driven by chip makers allowing their chips to operate at hotter core temperatures, right? And so again, this drives into the efficiency talk. It drives into the how do we adapt the chips to the going world, right? About 10, 15 years ago, everything was about battery life. Battery life has been kind of it's getting there. It's getting good. Displays are starting to become a big piece of that, right? And refresh rates and things like that. But when you look at ways you can drastically change efficiency in a model, maybe we run them a little hotter, right? Oh wow! All of a sudden, you can have these machines consuming less power for cooling. The fans can slow down around it. The heat sinks can change, right? Lots of things there's a lot of trickle down effects to that. So I feel like the chips are starting to do that as well. And that's driven by mobile applications as well. Nobody wants fans in their pockets, right? It's a killer. So removing heat and becoming efficient is not just driven by compute, but the markets as a whole.
So another question, can you talk about the technical challenges you faced when working with the wind developers or utility or the grid? And I think you hit on this a little bit, but if you could expand a bit on that, of how your data centers work with that.
Yeah, of course. And what's awesome is almost all of these folks have engineering departments, that we always want access to, or they always want access because we want to learn from each other. And so, they want to know how it works. They want to understand it, because there's things like reactive power. For those who don't know, there's real power and kind of what they call imaginary. When you take the square root of 1, it creates I. Well, there's all kinds of stuff with electronics, especially with AC circuits, that create that, what they call reactive power. And that's power that can change the overall efficiency of the grid, create heat, create mismatches and bounces and things like that. And the grid is very sensitive to understanding how these loads add. Now, wind farms add reactive power, right? Because they're massive energy generators that operate on AC motors, right? Well, DC, yeah. But the point is, they create this reactive power. So there's a lot of scrutiny into the kind of reactive power our data centers create, because we consume a lot of power. If we consumed all that power to run turbines, like run fans, that would create a lot of reactive power, but we don't. We run a lot of fans, but they're all behind protections, right? So we've architected our site to protect against these reactive power. And so that's just an example of something that a grid operator or an integrator is very, very keen to understand. And it's not really something you can understand unless you get really nuanced understanding of what's happening on the data center, right? And so those types of challenges mean that we have to get really good at communicating how the tech works and build that trust with our partners so that they trust it, that it's not going to freak out and create problems. These kind of loads, these massive data center loads, could really damage a grid if they're not controlled correctly, especially when they're turning on and off. Right? Like that's those two combinations, the fact that we're turning on and off and the fact that we are so big is why they enjoy these demos a lot, because they understand them, right?
And the flip side of that too is the ability to turn off means that when there's excess demand on the grid and they need power, you guys can ramp down quickly so that their other consumers can keep their lights on. They don't have to go through a brownout or anything.
Exactly. That's a big piece of value, right? And it's what we want to do. It's exactly why we exist. There's 100 other use cases for power that come before these data centers. And that's the beauty of the use case of, generative AI or any of these new use cases that don't need 100% low latency uptime. They just need a lot of compute. You can now provide that compute in a way that catalyzes green energy, right?
Yeah, that's the exciting part.
Yeah,
so we take a question from the audience. Do you need different computer technology or miners as you transition from mining Bitcoin to doing AI or other types of things?
Oh, that's a fantastic question. It is totally different. It's the miners that we use are Bitcoin miners. So they use single purpose chips called ASICs. And these chips are designed to do one thing, and that's the algorithm that mines Bitcoin. They'd be horrible doing anything else. And so if we want to go into AI ML, what you want are computers that are optimized for those use cases. And those are usually video cards, GPUs, and CPU cores and RAM and storage. So these things, they balance based on the different use cases out there. And now even more and more specialized chips are going to come out that do specialized kinds of AI, specialized kind of ML, especially with this generative AI starting to take off. There's going to be custom chips. Now, the beauty of it is the software has to adapt. So our data center is architected to accept any kind of computer. That's the beauty of it, right? If we pull out the Bitcoin miners and put in a bunch of AI ML rigs, GPU rigs, like the DGX systems by NVIDIA, the network, the cooling, the power architecture, all of it can quickly adapt to it. And the software behind the scenes will recognize it and change how it operates for that. And so that's the magic of this data center. It's really designed from the ground up to take advantage of the fact that chips are going to start changing fast and furious, and you need a home for them all that can accept it. Just like an Airbnb that's good for a party or a family, or just a couple. It doesn't matter. Yeah.
All right. And we're coming up at the end of our time. So I've got one final question. From a technology standpoint, what's the biggest challenge that you face as an industry and also as a company going forward?
Technology wise, I would say that the challenge is, it ties to what I had mentioned earlier, which is we are breaking a lot of what they, quote unquote, cardinal rules in the data center design industry, right? And in the power industry, right? And so when we do that, the technologies that we apply to do that, we have to make sure they're designed to do that, right? So when we apply firmware to a piece of mining equipment or to a network switch, we have to make sure that that piece of software is robust, for turning on and off, right? So that in and of itself is important, because the software that we're using, the hardware that we're using that we're not designing in-house, we have to make sure it's okay for this application, right? Because we're one of the first to do it. There's not a lot of published information. That's why we like to publish information as we get it. The second piece is proving to folks that you can build a data center that doesn't consume water, that can thrive in a highly remote environment, and works as advertised, can scale on and off. So just getting that social proof. And Dorothy's going to go a long way. Kentucky project does a long way of doing it, because we're turning that site on and off every day. The Dorothy site is going to make it a step further, because now we're interacting with the ERCOT grid, right? Which is another step. And we're co-located with a wind farm that has a curtailment problem, right? It's legitimately square in the mission of what we wanted to solve, which is wasted energy being consumed by a purpose-built data center that can accept any kind of compute.
Yeah, and that's exactly it. It's you guys are bringing the load to the power source. That's always been the challenge in the electricity industry, is that nobody wants the plants in their backyard, so you have to build the plants far away and bring the power to people. Here, you're bringing the demand right to that. So, well, great. Well, Dip, thank you very much. Really appreciate your time. This has been great. Thank you, everyone, for joining us. And again, there'll be a recording of this. Will be on our website and probably also on the Soluna website, and we'll be following up with a note. Thanks so much, everyone.